So how do we factor a trinomial? The same kind of quadratic three-term expressions that we've been working with. How do we navigate it when the leading coefficient is no longer 1? So what I want to do is start with the example here at the top of the page. 2x squared minus 5x minus 3. So the first thing that I want to look at is, there are a couple different methods we could use to approach this. And one of them, honestly, is the way that I learned how to factor these things when I was first learning algebra. And it's a very, in my opinion, slightly clumsy, not very clever way of trying to adapt the sum and the product rule to these kinds of problems. So this is what I might call the groping around in the dark method. Sometimes known as guess and check. In this method, what we would do is we would just try to use the same logic that we used when we did this with quadratic trinomials whose leading coefficient was 1. We would just slot in 2x squared, the leading coefficient, into one of our lattice boxes, negative 3 into the other. And then with 2x squared, my question is, how are we going to factor it? What are two factors that multiply together to give me 2x squared? Yeah, a 2 times a 1 is going to account for the 2. And then how does the x squared break apart? An x and an x. So that's how we would start this, again, what I call the groping around method, right? Where, at least in this example, because 2 is a prime number, there's only one way that we can split it apart into a pair of integers which multiply together to give me 2. And that's a 2 times a 1. So at least we know now that there's only one way to split apart the 2x squared. Now for the negative 3, what are the different ways in which I could split apart the negative 3? 3 and 1. And again, since 3 is prime, we're sort of boxed in, no pun intended, into choosing 3 and 1 for this process. Now, where the challenge comes in is that it will make a difference. First of all, it'll make a difference where I put my negative sign. One of these 3 and one of these 1s. One of those two have to be negative in order to make their product negative 3. But the other wrinkle that's introduced into this process that didn't happen before is it also is going to matter whether I put the 3 up here and the 1 down here, or whether I switch them, vice versa. Because one of those, well, let me put it this way. One of them is going to get multiplied by the 2, which is on my 2x, to fill in this square, and the other one is only going to get multiplied by 1x. So the symmetry that we used to have when we had an x and an x on the outside is broken. One of my x's now has a 2, and so now it matters where I put the 3 and where I put the 1. So the groping around in the dark method is just to take the 3 and the 1 and the negative sign and just try several combinations until we get to the one that we need. So you can imagine that if we were to combine all of my terms inside of my lattice, I'm going to get 2x squared, I'm going to get minus 3, but it's what I get in the middle that's going to be different, depending on how I arrange my 3, my 1, and my negative sign. So let's just try it the way that it's at right now, and I need to put the negative sign somewhere, so maybe I'll put it here. Okay. So if I put the negative sign right there, now let's fill out the rest of the grid and see if we got the right answer. So in this square, I'm going to have negative 3 times x, negative 3x, and in this square, I'm going to have 2x times 1, that's going to be 2x. And then when I add those two together, negative 3 plus 2 is going to give me minus 1. And so when I multiply these two together, I get 2x squared minus x minus 3. Two of the terms I got right. The term in the middle, I didn't. So clearly this is not the factorization that I wanted. So if I'm groping around in the dark, I'll rewind and say, all right, let me try again. Give me another run at this. Maybe what if I just move the negative sign over here instead onto the 1? Let's try it. So we'll go back and multiply everything in the table again. 3 times x in this square is going to give me 3x. 2x times negative 1 in this square is going to give me minus 2x. Now when I add those two together, I get positive 1x. And again, this product gives me two terms that I want and one that I don't. It gives me a plus x instead of a minus 5x. So that one doesn't work either. So I surmise, well, the problem wasn't where I placed the negative sign. The problem was in where I placed the 3 versus the 1. So then I go back and I say, all right, let's move the 1 up to the top and the 3 over to the side. And then maybe I'll have it. But then I still have the problem of which one do I put the negative sign on. So maybe I'll put the negative sign on the 3, just as a guess. Then when I multiply everything out, I get 1 times x, which is just 1x in this row, in this cell. But 2x times negative 3 is going to give me negative 6x in that cell. And now when I add x plus negative 6x, I get negative 5x, which it turns out is exactly what I wanted. So by groping around in the dark, I've come across a factorization for this. 2x plus 1 times x minus 3. So it took us sort of 3 different guesses before we got to this factorization. And we didn't have a lot of guesswork to work with, because we had a couple of coefficients, namely the 2 and the 3, which are both prime. So there was only one way to break them apart. Right? We can break the 2x squared apart in only one way. We can break the 3 apart in only one way. That's interesting. And yet it still took us several tries to get to where we were going. Now imagine if instead of 2 we had 6 in front of the x squared. Instead of 3 over here we had 48 or something. Now the list of ways that I could factor 6, well gosh, there's 3 different factorizations for the number 6. Actually, there's really only 2, but we can use symmetry on them and trade them around. 48 has half a dozen different ways to factor it. And so now I've got potentially this laundry list of dozens and dozens of different combinations that I would have to try if I'm groping around in the dark to do this. Doesn't mean you can't do it that way. It just means that it's probably not the most efficient use of your time. And on something like a quiz or an exam especially, time is a very precious commodity. So I think it's a good idea if we push this forward into a way that's a little bit more systematic. You can always try groping around if you don't remember the method we're about to talk about. But I like the method that we're about to do so much that it has replaced groping around in the dark for me completely in my process of how I factor these kinds of quadratic trinomials. It's called the AC method. So let's look at that next.